Hi Jennifer. So the first part of this montage will be the why there are elements piece. So we're going to start out and I'm just going to show this. It's going to have some protons and I'm going to say, hey, the thing that defines the atom or the element is the number of protons. And there also happens to be a number of electrons that matches this. Sorry, a number of neutrons that matches this, and so then this will say, okay, so this is the what defines the element, the number of protons, but there's going to be a matching number of neutrons, at least for 99% of carbon and for 96% of sulfur. But it's not always the case that the number of neutrons matches the number of protons, and that's going to really affect our spectra and throughout the class. Okay, Jen, so we just explained why there are elements, and now we'll go into why there is chemistry. And the chemistry is all about the number of electrons in holes. So it's all about the charges. So the number of protons is going to stay constant. And for carbon-12, the number of protons, which are positively charged, are going to be matched by the same number of electrons. So this whole thing has zero charge, it's neutral. But we can do something tricky and put in an extra electron. This is the extra electron. Then we have a net charge of negative, or we could take out an electron and create a hole, and we have a cation. These are going to become important because we can do this within the mass spectrometer to molecules, and we have to pay attention to it. And then we start building spectra. So I'm going to introduce a hypothetical small molecule here. It's C9S1. It's not chemically relevant, but it's good for these purposes. Going to show our carbon atoms, and I'm going to say, hey, the reason that there are spectra that we see are because there are isotopes, and isotopes are these heavier versions of the same elements. Note they have the same number of protons, they have different number of neutrons. I just forgot to add the neutrons and protons here, but and from now on I'll be showing you, I won't bother putting in the protons and neutrons, I'll just give them a color. So carbon-13 will be red. Carbon-14 is radioactive, and we don't see it very often. It's not very abundant, but carbon-13 is 1% of everything. So now we start this probabilistic modeling. We say, okay, imagine this molecule. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And if 1 out of every 100 carbons is carbon-13, how often will you see it? Well, let's just make this 10 molecules, and then if we do it that way, we see it once. And there's our little extra neutron hanging off. Well, if each time there's a sulfur, and 4%, so 4 out of 100 sulfurs are heavy, well, there you go. 1, 2, 3, 4 sulfurs. And, of course, if we do this by mass, then we would do this sexy thing where we take one of these little widgets here and bring it down and say, okay, that one goes there, this one goes there too, this one goes 2 away because that changes the mass by 2, and this one also goes 2 away, and this one goes there, and this one goes there, and this one goes 2 away, and this one goes 2 away, and this one goes right to 140, and this one goes to 140, this goes to 140, and this one goes 1 away. And so we have an extra hanging peak here, which I'll leave for now. And so that's the how to make spectra out of small molecules. And note that you see a large monoisotopic peak here, the thing with all light stuff, but only 2 little peaks over here. This one's a hanger-on. It shouldn't be there. And then we move up from small molecules to our next most important unit, and the second of 3, which is a peptide. Peptides happen to have around 100 carbon atoms. And so here I've just scrunched together those groups of 10, but keeping everything else the same. And you say, okay, so imagine a peptide that had 9 carbons and 1 sulfur. That's actually, that exists. And what would it look like? Well, we're just going to scrunch together all of our previous, which we've already modeled. And well, it's going to look like this. It's going to have an extra 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. And so you're not going to see any peak where it's all light or so-called monoisotopic. Everything's at 1309. And so this is another step in this probability modeling. And then we're going to expand this exact same concept. So these are these groups of previous groups of 100 from before and say, well, here's where we started. We had this group where we had this extra one, and we had these extra. Really, there should be another yellow one here, but this is the one we started from. But that's there, and it's the most abundant thing, and it makes the most abundant peak. But there's also, imagine, hey, you could have another carbon. That's certainly possible. Maybe you could even have 2 carbons, and that's possible, although a little bit less likely. Maybe you could lose a sulfur, so I would, you could lose a sulfur like that, and boom, there it goes. And so that weighs 2 less, and so and I'm not showing it here, but then each one of these would point down to its different place that it makes and make a composite spectrum. So because each one of these 4 has a different molecular weight, and so we can show, hey, this is where as you get larger with molecules, they get more and more peaks. And now we're ready to take these simulations to our principal player, proteins. So I'll introduce the students to this, which is a molecular formula, average molecular formula of an amino acid, and that's what makes up proteins. And then I'm going to say, all right, we've done models for different molecules. We're really going to think about proteins, and we have to think about this thing here. This is its molecular formula, and what it tells us is that the average amino acid has 5 carbons. Only 5% of amino acids have sulfur, and that's why this is so low. So the average amino acid doesn't even have 1 sulfur. In fact, it has 4 for every 100. So we say if an amino acid weighs 100 Daltons, a protein of 10,000 has 100 amino acids and therefore 500 carbons. And so I've drawn all 500 carbons here, and it'll have only 4 sulfur because, if it has 100 amino acids and 4 out of 100 are sulfur, well, here they are. So now we have our 1, 2, 3, 4 sulfur, and 4% of these, which is not very many, will be sulfur heavy. And then we have our heavy, and of course I've neglected to draw the second things, but we have our heavy carbon here, just like we did before. And so our average protein of 10,000 Daltons is going to have 1, 2, 3, 4, 5 heavy carbons, and maybe 1 heavy sulfur, maybe not. And so if we drew a spectrum, there'd be no monoisotopic peak. We'd go over 1, 2, 3, 4, 5, and our major peak would be 5 away. And I'll say, but hey, this isn't the only thing that can happen. There can also be this guy, which has an extra neutron. And it would, of course, weigh 1 more, and then, like this, we'll build up the spectra. And that's the idea. And then the final concept in this series is to say, okay, now we understand how molecules and spectra could be made. We have to understand that that's the real world, but we're going to put these into a mass spectrometer, and the mass spectrometer is going to do something to them. It might add an electron. It might take an electron away, therefore creating a hole. And most often it's going to add, and on rare occasions subtract protons. So then we'll come over and we'll say, so this is what the mass spectrometer does. Puts a proton on this. Well, guess what? Now it's 1 heavier, and you're going to have to account for that. And so then I would show this spectrum moving over 1. And then I would change the axis from mass to m/z, mass to charge. And I'd say, well, that's fine. And now picture all the things we just went through with peptides and proteins, and I'm going to say, well, for a small molecule, this is all that's going to happen. It's going to add 1. But when we combine these into 100 or even 500, well, there are going to be more protons adding 1, 2, 3, as many as 30 if it's 100,000 Daltons. So that's what the mass spectrometer is doing. So then we could say, well, sometimes maybe even on the same kind of peptide, maybe it adds, instead of 1, it adds 2. And now, instead of 1 peak, I'd have to make another peak at a different mass to charge ratio. And sometimes, instead of that, maybe it adds 3. Now this probably isn't going to happen with small molecules, but with peptides it's the norm. You usually see composite spectra composed of 1, 2, and 3 protons. Alright, John, thanks for your patience. This concludes I think our first attempt at this. Again, give me a call if you need anything or if there's anything that doesn't make sense. Thanks a million.